Hey Opties! Today we are talking about the Pythagorean Theorem, and we're going to look at it numerically and also with a trigonometric frame of mind. So let's go ahead and get started. The Pythagorean Theorem. This deals with only right triangles, so that's why we are reminding ourselves of this right angle right here. First, let's look at numerical Pythagorean Theorem. Here we have the formula, a squared plus b squared equals c squared. You may remember this from middle school and probably Algebra 1 and definitely geometry as well. Remember that c is always the side that's the longest side, and it's across from the right angle, and we call that the hypotenuse. A and B are both legs, just meaning they're not the hypotenuse. And notice that the smaller letter or lowercase letter is across from the uppercase letter that shows the angle. Here we have some Pythagorean triples. So A, B, and C, where all three are whole numbers, and they can make up the sides of a right triangle. So if you're working problems and you see that the hypotenuse is 5 and one of the legs is 4, you may not have to actually work the Pythagorean theorem to know that the other leg is 3, and so on. Just know that the longest side in each of these is the hypotenuse. Now let's find the height of this triangle using the Pythagorean theorem. So here is our formula. C is going to be our hypotenuse, of course, so we substitute 17 in for C. 8 could either be A or B. It will not matter because they're both legs, and we just substituted H in for B. Now we're just simplifying. 8 squared is 64, 17 squared is 289. Subtracting 64 from both sides. We get H squared is equal to 225. Now we take the square root of both sides. We get plus or minus 15, but we're only going to take the positive answer because we're talking about distance, and distance is always positive. So the height of this triangle is 15 units. This is another Pythagorean triple we had just seen on the previous slide. Now let's look at some trigonometric point of view of the Pythagorean theorem. This is very much different than what you've heard of probably in previous classes, but it's still the Pythagorean theorem. It's just using the ratios of side lengths in right triangles to do so. So first of all, we have three main trig functions: sine, cosine, and tangent. Sine is defined as the opposite divided by the hypotenuse in relation to whatever angle you're trying to find the sine of. So if we're setting here at theta, the side that is opposite this angle theta is side B. So that's why we have a B as our numerator. And the hypotenuse of this triangle is C. So that's why C is our denominator. Cosine is defined as adjacent divided by hypotenuse in relation to whatever angle you're looking at. So looking at theta, adjacent means beside, and yes, A and C are both sides that are technically adjacent to this angle theta, but we already know that C is the hypotenuse, so A is what we call the adjacent side. So adjacent divided by hypotenuse is A over C. Finally, we have tangent. Tangent of theta is the opposite divided by the adjacent, so B divided by A. And let's take a look at our point to ponder. So these ratios, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, can be kind of tricky to remember. So we can remember this by the acronym SOHCAHTOA. So SOHCAHTOA, so means sine is opposite over hypotenuse, ca means cosine is adjacent over hypotenuse, and toa means tangent is opposite over adjacent. Now we want to look at the Pythagorean identity. So using sine and cosine to write the Pythagorean theorem. So first we want to consider a circle with radius 1 with the origin as its center. We know that because we have the radius marked as 1, and we also see that the radius of the circle is 1 from all these points: 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And clearly the center of the circle is the origin because of those points. And we have a right triangle drawn here. We know that it's a right triangle without having the box because the x-axis and the y-axis are always perpendicular to each other, meaning they intersect at right angles. So if we're at 0, 0, the width of the triangle, or the base of the triangle, is x, and the height of the triangle is y. So if we're looking at this angle right here as our theta, sine would be opposite divided by hypotenuse. So it's y divided by 1, which is just y. Cosine is adjacent divided by hypotenuse. So it's x over 1, which is x. Now we want to apply the Pythagorean Theorem to this knowledge of that sine of theta is y and cosine of theta is x. So we could write it y squared plus x squared because those are our leg lengths. And that equals technically 1 squared, which is our hypotenuse, but we know 1 squared is 1, so we'll just leave it as 1. So y squared is sine squared theta, x squared is cosine squared theta, and of course we still have the 1 equals 1. So this is our Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. So let's take a look at a Khan Academy question called Use the Pythagorean Identity, and we're going to be given sine of some angle, which we see is in the 4th quadrant. So let's sketch that. 1, 2, 3, 4. This is the 4th quadrant. The signs, the positive and negativeness of all of these points are positive, then negative. And we know that cosine is x, and that's a theta sub 1, and sine is y. So the sine is negative, as we see here, and the cosine must be positive. Okay, well, one way you could do this, which is not technically using the Pythagorean identity, but it is helpful, it's more using the SOHCAHTOA. If we draw a right triangle, so here's our right angle, pick any old angle as theta, think about the numerator and denominator representing side lengths. So sine is opposite over hypotenuse. So the opposite side of theta is 24 or negative 24. Let's go ahead and make it negative. And the hypotenuse is going to be positive 25 since we've already taken care of our negative. And whatever is our width here is going to be the adjacent, and the adjacent divided by the hypotenuse will be our cosine. So we could use this, do the Pythagorean theorem, and get the base, and then just do base divided by hypotenuse, making sure this is positive, because remember, the cosine is positive. You got to make sure you're looking at your quadrants here. So that's one way if you'd like to use the Pythagorean theorem, just the numerical one. But we can use the Pythagorean identity like they're asking us to do. So we know sine squared theta plus cosine squared theta equals 1. So let's just substitute into this formula. So negative 24 divided by 25, all of that squared, plus cosine squared theta equals 1. So cosine squared theta is equal to 1 minus all of this stuff. So just using your calculator, you can square 24 and 25, and this is the fraction you get from that. Now we'll do 1 minus this fraction. Now we have figured out the fraction of 1 minus 576 divided by 625, and now we want to take the square root of both sides. And yes, We do the plus or minus when we take a square root, but we already know cosine is going to be positive, so we only need to take the positive. So we see here that the square root of 49 is 7, the square root of 625 is 25 because we just squared it to get to 625. And our final answer is 7 divided by 25. And it wants an exact answer, so just leave that as a fraction. And by the way, that means that the base of the triangle is 7 units. So let's check. And we are correct. All right, Opties, that's it for the Pythagorean theorem, including some trigonometry there. See you next time.